So last time, chapter 9, part 1, we left here, so we're going to move on. Another way to reduce triple bonds is through reduction of alkynes with metal ammonia. Shown here, metal being sodium and ammonia. In the presence of an alkyne, you can generate the transalkene, shown here. So to form the transalkene, 2 hydrogens must be added to the alkyne in this anti-stereochemistry. So its reduction is used to convert alkynes into transalkenes. In general, the reaction requires the use of dry ice to keep ammonium liquid, and then as the sodium metal dissolves in the ammonia, it loses an electron. The electron is solvated by ammonia, creating a deep blue solution, and so in the presence of ammonia and sodium, you then separate the charge where now you have an electron on the NH3. So that's important. So once you have that electron from the previous reaction, the first step is that electron will add onto that carbon. Note that's the half arrow because it's a single electron, but then the double bond breaks and then moves on to the carbon to form a radical anion. So this is a full arrow, and it's really important that you note that. While this over here is a half arrow. So in your mechanisms for your exams, just make sure you're distinct and clear that you have a half arrow just using electrons, and this is a full arrow because you're moving a pair of electrons. So now you generate a radical anion, shown here, right, with the negative charge residing on this carbon. Then you're going to have reaction with the ammonia. This will attack the hydrogen, electrons will go onto the nitrogen so that you generate the vinyl radical as well as this. And the next step is you're going to have another electron, so this is step 3, adds there, right? Again, it's a half arrow because we're looking at just a movement of a single electron. This will form the vinyl anion. Once you generate that vinyl anion, it'll pluck off a hydrogen from the ammonia, generating the transalkene. So it's really important that we generate the transalkene. So another reaction here is addition of 1 mole of halogen. So you can just add 1 mole of the halogen, being chloride or bromide, to an alkyne. This will generate addition where you have trans addition as well as cis addition, so you'll generate both products. That's important here. So if we do an example, adding 1 mole of bromine to this terminal alkyne will generate the trans as well as the cis product. So again, you're going to generate a mixture of the cis and trans isomers, and it's difficult to stop the reaction at the dihalide because oftentimes it'll go and reduce it all. So if you add 2 moles or 2 equivalents of chlorine or bromine, this triple bond gets reduced all the way down to the single bond. So as an example, here's 2 chloride, and then you have 2 moles of chlorides adding so that you just get the tetrahalide. So triple bonds can also react with acids HX in the form of HCl, HBr, or HI. It'll react adding on to the double bond, and then it'll react again, right? So that if you have a second mole of HX, it'll get fully reduced. So 1 mole, double bond, 2 moles, fully reduced single bond. So in general, you generate these vinyl halides, right, because you have it next to a double bond. 2 moles are added, you'll generate the geminal dihalide. And what's really key is that the addition is Markovnikov. So you have Markovnikov addition where the X will add on to the more substituted carbon, right? Even when you're forming, just when you're adding 1 mole versus 2 moles. And that's it. So in terms of mechanism of hydrogen halide addition, your nucleophile, which is your alkyne, will pluck off that hydrogen, kick off the X, or the halide, and then we'll generate the vinyl cation, in which the carbocation is on the more substituted carbon. Then you have the halide come in, attack that, generating the added product, the vinyl halide, in the Markovnikov orientation. So in general, the proton adds to the least substituted carbon, forming the vinyl cation, which then allows for the Markovnikov. You can have anti-Markovnikov additions of hydrogen bromide to alkynes if you add the a peroxide. So ROOR is a peroxide. By using these peroxides and in addition of HBr, you can have anti-Markovnikov addition. The bromide will attach to the least substituted carbon, right? Giving a mixture of cis and trans isomers, but it will give you anti-Markovnikov addition. So that's really important. For hydration of alkynes, mercuric sulfate and aqueous sulfuric acid adds HOH to one pi bond with a Markovnikov orientation, forming a vinyl alcohol or enol. This then rearranges to a ketone, important. And for hydroboration oxidations, water addition, or HOH, adds in an anti-Markovnikov orientation and rearranges to form the alcohol. So in the case of mercuric ion catalyzed hydration, in the presence of water and mercury, H2SO4, you're going to have Markovnikov addition, right, where the OH is on the more substituted carbon. In the presence of protons, will rearrange from this enol, right, to a ketone. It's analogous to the oxymercuration, demercuration of alkenes. Hydration is catalyzed by this mercuric ion, and a mixture of mercuric acetate and aqueous sulfuric acid is used. You generate the vinyl alcohol or the enol, which tautomerizes to form the ketone or aldehyde. So starting with the alkyne, your source of electrons will react with the mercuric ion to form the vinyl carbocation, shown here. Then the water will attack that carbocation to generate the water adduct. Water will then pluck off the hydrogen, neutralizing it to generate the organomercurial alcohol. After hydrolysis of the alcohol, that will remove this mercury, forming the vinyl alcohol, commonly known as the enol. So in terms of the mechanism of replacing that mercuric ion, it goes like this, where you have electrons from your double bond being protonated, forming the carbocation. Then this undergoes resonance stabilized in intermediate formation, in which, shown here, electrons from your oxygen, from the OH come down to form the double bond. Once that's formed, you have mercury. Electrons from the mercury go in and form the CC double bond, and then electrons go back to quench that positive charge, generating your vinyl alcohol ether, or enol. So once you form your enol, this undergoes keto-enol tautomerization, where instead of the enol, you generate the keto form. Enols are not stable, and they isomerize to the aldehyde or ketone. And this is an important terminology, keto-enol tautomerization. So, mechanism of acid catalyzed tautomerization. First, you have addition of a proton at the methylene group. So your source of electrons is over here. Protonates generating your carbocation. Now this undergoes keto-enol tautomerization, in which you have electrons from your oxygen come in, right? Form that double bond. So here's your tautomer, right? Over here. And then once you form your tautomer, you're going to have loss of that hydrogen, where you have electrons from water pluck off that hydrogen, quench that positive charge, forming the ketone. In general, to move a proton, as in tautomerization under acidic conditions, you want to add the proton in a new position, then remove it from the old position. Hydroboration oxidation also can react with alkynes in the presence of this diacetyl borane will form a vinyl borane, and the Sia group here is just secondary isoamyl or siamyl, shown here. In hydroboration oxidation, as we've seen with alkenes, it undergoes anti-Markovnikov addition. And then a hindered alkyl borane must be used to prevent two molecules of borane from adding the triple bond. So that's why we use this diacetyl borane. So in terms of the mechanism, you have, once you generate the vinyl borane in the presence of peroxide and base, you'll generate an enol, which under basic conditions will generate the aldehyde. So this second step, which is in the presence of base and peroxide, will essentially replace the boron with DOH, and once that enol is formed, it tautomerizes to the aldehyde. So in terms of the mechanism for base catalyzed tautomerization, the base hydroxide will pluck off that hydrogen, electrons will go to the oxygen, and then it'll undergo resonance again on brackets. And now, which is not shown, which I'll show you now, you have electrons from the oxygen go down here, and then the electrons go onto the carbon to generate the stabilized enolate ion. Once you have the stabilized enolate ion, your electrons from that carbanion will pluck off the hydrogen, generating the keto form. To move a proton, as in a tautomerization under basic conditions, what's important is you want to try removing the proton from its old position, then adding it to the new position, akin to the acidations. Oxidation of alkynes, it's similar to the oxidation of alkenes as we had seen in the previous chapter. It's you can use dilute neutral solution of potassium permanganate. These will oxidize alkynes into diketones. If you use warm basic potassium permanganate, this cleaves triple bonds, and ozonolysis followed by hydrolysis also cleaves the triple bond. So permanganate oxidation, you've seen the mechanism in detail. This is just showing you what happens without looking at the mechanism. And when you're adding potassium permanganate in water, you're going to have, you're going to have water being added on, and then you're going to have loss of water to generate the diketone. So under neutral conditions, a dilute potassium permanganate solution can oxidize a triple bond into a diketone, and it uses aqueous potassium permanganate. So permanganate oxidation of alkynes to carboxylic acid. So now if you go and add basic conditions and add heat to the system, this is going to cleave, that triple bond, so that you generate the acids on each side. Once you protonate, this will generate from the acetate ions to the acetic acid and propionic acid. So in terms of ozonolysis, ozonolysis of alkynes produce carboxylic acids. When we did alkene ozonolysis, it gave aldehydes and ketones. So in the presence of ozone, a triple bond, and then subsequently water, you generate the two acids. So it's going to cleave this to generate the two acids. So either this permanganate cleavage from the previous slide or ozonolysis can be used to determine the position of a triple bond in an unknown alkyne, because on one end, if you had R versus H, you would know that you generate this. And this will decompose. All right, so this ends chapter 9. Again, there's a lot of mechanisms that I've went through, and many of them similar to alkene mechanisms, so they're not fully shown out, but you should be able to do that on your own.